Right, so the session in this room is Grapherium Python module for very large sets of graphs. Our speaker now is Mr. Takeru Inoue, who is the Iterators researcher and also working for a telecommunication company. And he founded several software projects like DNet and RCDN.info. Please welcome our speaker now.
Thank you, Chair. I'm Takeru Inoue from ZDD Iterators Minato project, which is a national research project on computer science in Japan. And this is joint work with Iwashita-san, Kawahara-sensei, and Minato-sensei. Okay. My talk is about Graphillion, a new My talk is about Graphillion, a new Python module that efficiently handles very large sets of graphs, and it solves various graph problems like optimization, verification, and statistics. Before getting into Graphillion, I'd like to show you a short movie about our project. The movie can be a very good introduction to Graphillion. I think some of you have seen the movie. The movie was getting very popular last year, and it has been played more than 1 million times on YouTube. Okay, let's start. Can you see the English superscript? If no, I'll read it. No? Today, let's study how to count combinations. Okay. In this square, how many ways are there to go from S to G? 2 ways. That's right. How many ways are there if we divide the square into 2 by 2? You can take the long way around, but you can't go to the same way twice. 6 ways? No. There are 12 ways. Yes, let's try counting the number of paths. In this way, they continue to count the number of paths at first by manual, and then using a PC, and finally they use a supercomputer. But even with the supercomputer, it took about 4 hours to count the number of paths, 4 hours, on the 8 by 8 grid graph. Okay. And they will challenge the next step, the 9 by 9 grid at last. Okay, 9 by 9 grid. What will happen next? It may take 2 or 3 days. Today we will have a throughput over. Yum, yum. Six years later, from the teacher, the results are in. Please come right now. My children, you've grown. Let's begin the class. Teacher, when the square is divided into 9 by 9, there are many ways. I'm starting to feel dizzy. Dizzy? But it's been 6 years. Next is 10 by 10. Wait a minute. For 8 by 8, the calculation took 4.5 hours, and for 9 by 9, it took 6.5 years. That's right. The last calculation took more than 10,000 times. That means you already died. Don't do it. I know. I want to demonstrate how amazing combinatorial explosion is. Please don't stop it. Teacher. $250,000 years later. We finally have the result when the square is divided into 10 by 10. There are many ways. I must contact the children's descendants. Hello, children's descendants. This is robot teacher. When the square is divided into 10. What? You have the wrong number. Okay, next is 11 by 11. Counting 11 by 11 is the same way. It will take 29 billion years. Okay. It's very interesting, isn't it? Okay. Please look at, wait a minute. No. I'd like to stop the last picture. Okay. Please look at this superscript. Okay. It says, if we use the latest algorithmic techniques, we can solve this problem just in a few seconds. This means 250,000 years can be reduced into just a few seconds. It's amazing. Aren't you interested in the latest algorithmic techniques? That's Graphillion. By the way, I think you are wondering why we created such a funny movie and why we developed a software library like Graphillion. As I said, our project is an academic project. And so we are supposed to write academic papers, not funny movies or software library. So here, please let me introduce our project briefly. Oh? Okay. Our project is officially named Minato Discrete Structure Manipulation System Project. And it is an academic project on computer science. There are more than 15 researchers in the project. It is located in Sapporo, the northern part of Japan. We are studying many new algorithms in the project, and we believe they are pretty powerful and useful. We hope our algorithms will be widely used to solve real and important problems of our society. I mean, I'd like for practitioners like you to fully utilize our algorithms in order to solve your own problems. But unfortunately, the algorithms are very complicated and not easy to understand. Of course, we published some academic papers describing the algorithms, but they are basically written in mathematical jargon, and so it doesn't seem helpful. So, what we need is not only mathematics, but also a working code with clear abstraction. This is the reason why we developed Graphillion. We give graph abstraction to our algorithms and integrate them into a unified software library. A graph is a well-known data structure that represents a set of vertices connected by edges like that. It is often used as a mathematical model to represent many important problems. We believe graph is the best abstraction in terms of trade-off between understandability and generality. Actually, some of our algorithms are more general and not limited to graphs, but we chose the simplicity of graphs rather than excessive generality that often involves complicated mathematical discussion. What's more, by giving the unified view on our algorithms, which were actually developed separately originally, we now realize an integrated, powerful framework to solve hard graph problems. Of course, we already have many graph tools. There are many graph tools in the world. Why did we need to develop another graph tool? Because the existing graph tools are designed to handle just a single graph at a time. But we actually have to care a set of many graphs to solve complicated real problems. I think you are not familiar with the concept of a set of graphs, but it comes with any graph when you consider multiple subgraphs cut from the original graph. For example, considering possible driving routes on a road map, or examining feasible power flows on a power grid, or evaluating patterns found in a chemical reaction network. Unfortunately, the number of subgraphs increases exponentially with the graph size. And so it would take 1 million years to examine all the subgraphs without efficient algorithms, as I demonstrated in the introduction movie. Graphillion provides efficient algorithms that handle a huge number of graphs. Graphillion is named after millions of trillions of graphs. It can be used to solve a variety of graph problems, such as optimization, verification, and statistics. Now, I'd like to show you a demo movie and give detailed comments during the demo. Okay. The demo is, I believe, amazing, but it was taken on a normal computer, not on a supercomputer. Okay, here we go. It begins with a review of the introduction movie. If she'd known Graphillion at that time. Let's play with Graphillion. Okay, we now import GraphSet class from Graphillion module. Okay. Here, let me introduce some objects used in Graphillion. In Graphillion, a vertex is represented by any hashable object, like a number, a string, or tuple. An edge is a pair of vertices, or technically, a tuple of two vertices. All edges must be undirected in Graphillion. Graphillion also supports weighted edges. In that case, a tuple includes a weight value like that. Oh, sorry. A graph or a subgraph is a list of edges, and a set of graphs, that is our focus, is represented as a graph set object. Graph set object. In this example, the graph set object includes two graphs or two lists of edges. Okay, let's continue. Graphillion.tutorial is a helper module for the demo. It provides useful functions like Grapherium. Okay, so this is a very important point. We have to set the universe graph at the beginning in the use of Graphillion. Graphillion finds subgraphs just within the given universe. If you use an edge not in the universe, an exception is raised. In the top example, in this example, the small universe has only 12 edges. And the 2 to the 12th power of subgraphs are handled by Graphillion. In the demo, we use the 10 by 10 grid graph as our universe. This large universe has 220 edges, and so about 10 to the 66 power of subgraphs must be handled by Graphillion. Okay. This is a big challenge. Okay. In my talk, I don't distinguish the word subgraph from the graph and use the both interchangeably. Okay. We will find paths on the grid. Okay. In the grid, vertices are simply named like 1, 2, 3, and up to 121. So the starting vertex is 1, and the goal is 121. Okay. We've got a new graph set object that stars all the paths between the start and the goal. Graphillion provides 3 ways to create such a new graph set object. This is one of them. Let me describe the 3. The first is graph list. This is the most straightforward way to create a new graph set object. It specifies a list of graphs and gets a new object with the specified graphs. In this example, 2 graphs, one has a single edge and the other has 2 edges are given. And a new graph set object with the given 2 graphs is created. If no argument is given, it is regarded as an empty list and we have an empty set. The second is edge constraint. Edge constraint specifies edges to be included or not included in the new object. The constraint is given by a dict of edge list. Edges not specified in the dict are treated as don't care. That is, they can be included and not included in the new set object. In the example, edge 1, 4 is included, and edges 1, 2, and 2, 3 are not included in the new object. Other edges, like 2, 5, don't care. Okay. An empty dict means, the bottom example, an empty dict means no constraint. Thank you. Okay. No constraint is given. And so the new graph set object includes all possible subgraphs on the universe. In this example, the universe has 7 edges, and so the 2 to the 7th power of subgraphs are stored in the new object. Okay. This is so-called a power set of edges. The third is graph type. We can specify a graph type, such as tree or path, and create a new graph set object that stores all subgraphs matching the specified type. The first example finds all paths between vertex 1 and 6. And the second example finds all the spanning trees on the universe. Here, a tree is a graph that has no loop, and spanning means all vertices are covered by edges. Okay, let's continue. Here we use LEN method, L-E-N method, of the graph set object path to count the number of paths stored in this object. We can also use Python's built-in len function to count it. Actually, Graphillion follows the interface of Python's built-in set completely, and this means it's very easy to learn. All of these functions and methods are supported by Graphillion. For example, built-in len function and set operations like union and intersection, and so on. Of course, its internal implementation is different with the built-in set, and we believe Graphillion is much more efficient. I'd like to give a caution about the use of built-in len function with Graphillion. Technically, the built-in len function can overflow for a very large set because it relies on 32-bit integers. This limitation is acceptable in the normal case, but not acceptable with Graphillion because Graphillion can store a huge number of graphs beyond the 32-bit limitation. This is the reason why Graphillion provides its own len method. It never overflows because it uses long integers of unlimited precision. Okay, let's continue. Now counting. Okay, now we've counted the number of paths. It's very quick, isn't it? Remember, it took 250,000 years in the introduction movie. Oh, the teacher said, "Thank you from the heavens." This graph set object, named paths, stores the set of paths in the compressed form. Yeah. The paths are stored in a compressed form, and so it requires surprisingly small amount of memory. In this case, it requires about only 400 megabytes. This great compression ability is the key of Graphillion. Okay. We can retrieve the stored paths one by one from the graph object with an iterator, but of course it takes years, and we stopped it now. And anyway, Graphillion provides various iterators, and they are much more. Graphillion provides other iterators, and they are much more helpful for such a huge set. But I'll describe them later. Let's continue. Okay, now we've done a warm-up, and in the rest of the demo, Graphillion will tap its potential and will solve more interesting problems. The next problem is like this. We first pick up the key at vertex 100, and then open the treasure box with the key at 22, and finally get to the goal. We are not allowed to pass through the same vertex twice. Okay. How to select all the such constrained paths? It's very easy for Graphillion. First, we find paths to the key that do not pass through the treasure box by using the excluding method. And then we select successfully exiting paths from the object named paths that stores all the paths between the start and goals. Okay. Finally, we put the constraints on the start goal paths by using the toIncluding method in order to cover one of the keys paths and to pass through the treasure box 22. Okay. In this way, we can select a set of graphs by the rich algebra of Graphillion, like including and excluding methods. This is a key feature of Graphillion, and this allows Graphillion to deal with complicated constraints like that. Here, I will describe the graph set algebra in detail. As I said, Graphillion provides normal set operations like union and intersection, as Python's built-in set does. In addition, Graphillion defines new operations designed for sets of sets. The including method, which were used in the previous demo, selects supergraphs of a given object. Here, a given object can be a graph set, a graph, an edge, or vertex. In this example, supergraphs of the right-hand graph are selected. Okay. This is a supergraph of that, and this is not a supergraph of that. So this one is selected. Okay. The excluding method returns a set of graphs that don't include a given object. And okay, the included method returns subgraphs of a given object. We can also select graphs by their size or by minimality or maximality. Graphillion also supports modification methods, like adding edges to all the graphs in a set. That's graph set algebra. Okay, let's continue. Next, we will conduct statistical analysis with Graphillion. We randomly select 1,000 sample paths from the successfully exiting paths. And count the number of turns for each selected path. Count the number of turns. This is a histogram of the turn counts. Against our instincts, most of the paths makes many turns, around 60. Here we used the random iter for the random sampling. Graphillion provides 4 types of iterators. I'll describe them in detail. The default iterators simply iterates over graphs. This is the fastest iterator in Graphillion, and the random iterator selects a graph uniformly randomly, and so it can be used for the random sampling, as I demonstrated in the previous demo. The minimizing and maximizing iterators return graphs in the ascending and descending order of graph weights. In this example, edges have weights like this. The maximizing iterator returns the graphs in descending order like this. The most weighted graph comes first. We can use these minimizing and maximizing iterators for the optimization and the top case search. Here, the optimization usually requires just a single top graph, and while top case search requires k graphs in the top. We will use the maximizing iterator for the optimization in the rest of the demo. We select parts by their size, 40. This is another graph set operation as I explained. Okay. Before moving into more practical problems, next problems, let me describe Graphillion internals. Graphillion is implemented as a Python module with C extensions. Actually, 80% of code is written in C and C++, and only the graph abstraction is provided by Python. In the Python world, a programmer first creates sets of specified graphs and then manipulates them with the rich algebra. Finally, she retrieves some necessary graphs using various iterators. These operations can be simply written in Graphillion. In the internal, I mean C and C++ world, a graph set is represented as a compressed form, as a compressed data. Only the reference to a set is exposed to the Python. And graphs in the set are hidden from the Python. The rich algebra is performed without decompressing the set. And so it's very efficient. Iterators restore only necessary graphs without restoring all graphs in the set. It restores only necessary graphs. I'll describe the compressed data structure, which is used to represent a set of graphs. We use a data structure named zero suppressed binary decision diagrams, or simply ZDD. A ZDD was originally developed to represent a set of simple sets. Set of sets, not a graph. Here we assume we have three elements, A, B, and C, and we have three sets, A, C, B, C, and C. A set of sets can be a collection of these sets. Okay? This is an example of a set of sets. Here we assume these elements, A, B, and C, are graph edges. Then a set of sets is regarded as a set of edge sets or set of graphs. Now, in this way, we can employ ZDD as a compression means for graphs. ZDD's compression mechanism is very simple. The right top figure is a non-compressed binary decision diagram. Each node is an element, and each path from the root represents a set. A solid arrow indicates the element is included. And a dotted arrow represents the element is not included. Okay. For example, the red path means A is included, B is not included, and C is included. And so the red path represents a set AC. The whole diagram shows a set of sets or set of edges. AC, and BC, and C. Where one at the bottom means the path is valid, and 0 means the path is invalid. This diagram, this non-compressed diagram, can be compressed into the bottom one without any information loss. ZDD's compression ability is very awesome. For example, 10 to the 24th power of paths in the demo is represented by only 1 million ZDD nodes. In addition, we have efficient algorithms that perform the rich graph set algebra without decompression. We can create a very complicated ZDD by combining several simple ZDDs with the algebra. Unfortunately, we have no time to discuss ZDDs in detail, but this is the key of Graphillion's great efficiency. Okay, now we get back to the demo. The next problem is analysis of power distribution network, much more practical problem. We use a simple power network model in this demo. In the simplified network, houses, each vertex, are connected to four power sources by power lines, graph edges, like the left-hand figure. Okay. The power flow or route of the power delivery is configured by switches placed on each line. Each line has an electrical switching. The power must be transmitted to all houses, and the power flow must not have a loop to protect short circuit. And so mathematically, the power flow forms a spanning forest. Here, a forest is a set of trees. Like this is an example of a spanning forest. Each tree in the forest must be connected exclusively to a power source. Each tree must be connected to power source. The amount of power transmitted from a single source is strictly restricted for the secure power flow. And so each tree must be smaller than its capacity. Okay, let's get back to the demo. There are tree-like routes. Wait a minute. Okay. This is a tree-like path from power source to all houses through lines. Restrict the maximum power per source less than 30 houses for the line protection. Find all but unsecure cases with too much power by using the algebra. Select secure routes without the unsecure cases. We finally found all the secure power flows like these. Okay. This is an example of power of the graph set algebra. Okay, we move to the optimization problem. The current unsecure power flow, wait a minute, not shown yet. Okay. Okay. The current unsecure power flow in the left will be changed to a secure one in the right with least switching operations. So that is, we will minimize the switching operations executed through the network transition. Okay, now here we give a negative weight. We give a negative weight to a switch that has been reconfigured and maximize the total weight. Sorry, it's a little confused. In this way, a secure power flow that requires least switching operation is found like this. I think both are quite similar, but this one is secure. Okay, this is the final demo. We use the blocking method to find dangerous failures that disable the secure power delivery. I'll describe this kind of verification in detail in the next slide. Okay. Before describing verification, let me describe a failure in a power network. In order to deliver the power, we don't use all lines at a time. only use some of lines to deliver the power. If a few lines were cut by accident, we could deliver the power using other lines by reconfiguring switches. However, there is a set of lines commonly used all the secure power flows. If all lines in such a set were cut, non-secure power flow could be reconfigured. Mathematically, such a set is called heating set or blocking set. In this example, three secure power flows can be configured in the above network. One uses line 1, 3, 4, 6, and next secure power flow uses 1, 2, 5, 6, okay, like that. All flows use line 1 or 4. And so if lines 1 and 4 were cut, we couldn't deliver the power securely. If lines 1 and 4 cut, we couldn't realize any of them. This is an example of a blocking set or heating set. We have to remove such blocking set from the network completely for the reliable power delivery. By the way, do you remember how many secure power flows are there in the demo? This is only 3, but there are about 7 trillion secure power flows in the demo. And so we have to find all blocking sets over the 7 trillion power flows. This is a very tough problem, but Graphillion found all of them just in a few seconds, as I demonstrated. In this way, Graphillion can be used to verify complex systems like a power grid. Okay. There are some topics I didn't mention in my talk. I omitted the installation process because it's very easy. Just type easy install Graphillion, that's all, if you have GCC on your system. Graphillion supports all major operating systems, including Windows. Graph object of network X can be used with Graphillion transparently. Details are shown on Graphillion's website. Please see that. Graphillion implements many interesting algorithms, though I didn't discuss them in my talk, sorry. For example, dynamic programming. Dynamic programming is used for the optimization internally. I didn't mention the performance issue. It's not easy to understand how to improve the performance of Graphillion, but now I give a hint here. The key is the order of edges when setting the universe. Try to find the best order of edges, and the performance might be improved drastically. Graphillion is a newborn module, but it already has some applications. Power network analysis is one of them. And Graphillion is also used for road network analysis, logic puzzle solvers, and so on. And I think it can be good teaching materials in a class of computer science. Okay. Finally, let me conclude my talk. Okay. I introduced our Python module named Graphillion. Graphillion handles a huge number of graphs using a compressed data structure named ZDD. The rich algebra manipulates huge graph sets efficiently, and so we can tame complicated constraints. Graphillion provides useful iterators, and so we can retrieve only necessary graphs from the huge set. And so Graphillion can be used for various graph problems, including optimization, verification, and statistics. Okay, finally, I'd like for you practitioners to tackle with your own problems with Graphillion. This is the reason why we provide a working code that integrates our algorithms. I think Graphillion is best used for problems that require high accuracy, because Graphillion performs exactly without any approximation. in other words, Graphillion knows the exact shape of a set, and so it can count the exact number of graphs in a set, as I demonstrated. Graphillion is found here, so please access here, graphillion.org. Thank you.
Thank you. I'd like to know if anybody has a question.
Hi, thank you for your great presentation, and I'm really interested in your library, Graphillion. And then, if you have any actual the samples or actual showcases of the use case of the Graphillion, could you share the some?
Okay. One example is power network analysis, as I mentioned, and. In my talk, I showed. Today, I used a simplified power network, but actual power network analysis is more complicated. It includes some power flow calculation, like current and voltage and three-phase. So this is one example, and I think this is the most successful example so far. And wait a minute. And other example includes a kind of road map analysis for evacuation from natural disasters. So we have to care many patterns of disruption on the road. So we have to enumerate subgraphs. And another example is railroad analysis. And our project has a guy who loves rail systems, railroad, and he uses Graphillion to analyze railroad, for example, to find longest way to go to the destination or something like that. And yeah, that's all I know, and I can tell you here. But I believe Graphillion can be applied to other fields, like maybe chemicals or bioinformatics or something like that. So I'd like to show you to use Graphillion with your own program. Okay.
It's a very exciting presentation. So do you know assessment problem to NP complete a belly head weight? So your approach is theoretically proved.
Yeah, actually.
It's a NP complete problem. You are solved.
No.
It's exciting, yeah.
No.
Wow.
Not at all. Yeah, actually, the worst case is, of course, exponential. But
your approach is proved mathematical or theoretically proved is damned.
Sorry,
Theoretical.
Theoretical. And,
yeah.
No. Our approach, main interesting our project is not theory but practice.
No theory. I was no theory.
No. Yeah. What I will
how to
tell
prove your
no.
result? How to check your problem?
You mean how to check if our result is correct or our
Problem must be theoretical proof and actually checked to each coding system must be checked. Yeah. How to debug your system theoretically and debugging or actually code.
Sorry, I can't catch your
point. You are saying it's very, very exciting result. I work with CAD-WAX, the graphics problem or layout issues. Many guys died to CAD CAD frameworks where you have no theoretical result, I guess. You are exciting result you're showing now.
Yes. You are interested in computational
Yes.
algebra. Okay. Yeah. So, I want to tell you some theoretical result on computational issues, but we know the Graphillion works well in most practical problems, but still its worst case is not bounded. Okay, that's
So I'm an application engineer, so I know your limitation of a system, the application limitation. There's no perfect algorithm there. Many algorithms have a restriction.
yes.
So what your restriction to application?
Okay.
What the assumption to application?
Okay, I've got your point. So, actually, there is no tight restriction, but
No, restriction is perfect.
no,
Hey,
but
Actually, we're kind of out of time, so if you can talk after.
You are doing a very good job.
thank you, thank you. But yeah,
To restrict your pre-high. You can get to a lower.
All right.
There is no.
All right.
Special.
Well, thank you for your comments. Okay, well, thank you for your presentation.
thank you.